Welcome back, students. We are back with another part of your lesson number 24. In our last class, we have discussed how your astronomical telescopes forms the image of an object which is placed at infinity. Fine. Now, in today's class, we will derive the magnifying power of the astronomical telescope. Now, before we derive the magnifying power of the astronomical telescope, let us set some conditions. Fine. So, the first condition is that the object should be placed at infinity. Okay. Now, if the object is at infinity, okay, then the rays coming from the objects forms an image at this point. Okay. Now, the next condition we'll set is this image should be formed at the focal length of the objective. Since the object is placed at infinity, that's why the image should be formed at the focal length. Fine. So if I have to show this here, if this point represents the focal length of the objective, then this distance represents the focal length of the objective. Fine. Now the next, what happens? Next we put a eyepiece so that this eyepiece forms the image of this virtual object at this point. Now the condition of this eyepiece was that the object or this virtual object should be placed beyond the focal length of the eyepiece in order to form a final image. Fine. Now, the final image is formed at the least distance of distinct visions. That means the distance up to which our eyes can see clearly. If the image is formed somewhere beyond this distance, what happens? We cannot see the clear image. Hence, this D denotes the distance up to which this image formed can be seen clearly by our human eye. Fine. Now, let us now discuss the magnifying power. So according to the definition, the magnifying power of an astronomical or your telescope or simple telescope, the magnifying power of telescope is defined as the ratio of the angle subtended at the eye by the final image formed at least distance of distinct vision to the angle subtended at the eye by the by the object placed at infinity. Fine. So let us suppose this is your object. Okay, this object subtends some angle. Fine. So let us denote this angle as alpha. Okay, I'll use yellow pen to for objective. Okay, for objective lens I will use the yellow pen. Okay, so if this point is the center of the objective, that is, this is the optical center which is represented O, then it makes the angle alpha. Fine. Fine, this makes angle alpha with the rays coming from the distant objects. Fine. These are the rays which are coming from the distant objects, and it makes an or it subtends a angle alpha. Now, as you know that suppose if there are two lines intersecting each other, okay, suppose there are two lines intersecting each other, then in that case this angle should be equal to this angle by the property of vertically opposite angles. Fine. Similarly, we'll use this concept here. This angle alpha should be equal to this angle. Fine. So let me mark this angle as alpha. Okay, fine. Now consider another angle, the angle which your final image forms at your eyepiece. Fine, this angle. So this angle, suppose this is your eyepiece. Okay, for eyepiece I will use a red pen. So this is the center of the eyepiece, and this image makes an angle beta. Fine. Okay. Now coming to our magnifying power. The magnifying power states that the magnifying power is the ratio of the angle subtended at the eye. Okay, now this time consider your eye to be placed somewhere near the eyepiece, since we are looking through the eyepiece. Okay, so instead of considering this position, consider this one as your eye for now. Why is it so? Because we are looking through this eyepiece. Okay, now if you see what is the angle subtended by the final virtual image or the final image makes an angle beta. Fine. So magnifying power states that the ratio of the angle subtended by the image to the angle subtended by the object. Now, if you look carefully, your object AB is placed at infinity. By infinity, it means it is placed very, very far. So since the object is placed very, very far, okay, so in that case, okay, you can consider this distance negligible in comparison to this distance, the distance between the object and your objective. Okay, so what I'm saying is that suppose this is the object which is placed at infinity. Okay, it makes a ray. Fine, it forms a ray, it falls on the objective. After this it falls on the eyepiece. Now if you see carefully, okay, this distance, the distance between the objective and the eyepiece, this one denotes your objective and this lens denotes your eyepiece. Now if you see, this distance is very small in comparison to the distance between the objective and the object. So in such case, what you can do is you can simply ignore this distance. Now, why I'm telling you to ignore this distance? If you ignore this distance, what you can assume is that your human eye, okay, your human eye can be placed at your objective. Fine, like this. Okay, why I'm telling, am I saying so? Because this distance, the distance between the objective and the eyepiece is very small as compared to the distance between the telescope and the object. So in such cases, what we can do is we can assume that our eye is somewhere near the objective. Fine. So if our eye is placed somewhere here, then what is the angle subtended by the object at our eye? It is alpha. Fine. So magnifying power states the ratio of this angle beta by angle alpha. Fine. So from this figure, let your angle A dash OB dash be your angle alpha, and your angle A dash EB dash be your angle beta. Fine. So let us write down this one first. Fine. So for the objective, I was using the yellow pen. Okay. So for the objective, let angle A dash O B dash A dash O B dash equals to your angle alpha. Fine. And for the eyepiece, for which I was using red pen. Okay. Let me just check. Yes. So for the eyepiece, the angle A dash O B dash, sorry, it is angle AEB. Okay. A dash E B dash represents the angle beta. Fine. These are the two angles. Then what will be your magnifying power? The magnifying power M can be written as the ratio of the angle subtended by the image. And what is that angle? Beta. So I'll write down beta first, divided by the angle subtended by the object, which is your alpha. So next I'll write down alpha in the denominator. Fine. Now, since your beta and alpha are very small angle, okay, I'll write down here, since alpha and beta are small angles, fine. If they are small angles, then in that case, I can write down my beta as tan beta approximately equals to tan of beta, and my alpha as tan of alpha. Fine. Now, let us see what is tan beta and what are tan alpha. Now, coming back to our figure. For tan beta, what you can do is you can consider this red triangle. Triangle A dash E B dash. Fine. Now, from here, what will be tan beta? Tan beta will be the ratio of the opposite side. Fine, in this triangle, which is the side opposite to beta? It is A dash B dash. So tan beta equals to the ratio of the opposite side upon adjacent side, which is B dash E. Fine. Similarly, for alpha, For alpha, you can consider this yellow triangle, okay? For alpha, consider this triangle. Now, now here also you can write down for tan alpha, the ratio of the opposite side A dash B dash upon the adjacent side, which is O B dash. So from the figure, I can write down my tan beta S equals to tan beta was the ratio of the opposite side A dash B dash by the adjacent side B dash E, right? Or I can also write E B dash. Similarly, your tan alpha can be written as the ratio of the opposite side A dash B dash upon the adjacent side, which is O B dash. Fine. Now, in this triangle, look here, this AB dash and AB dash can get cancelled. Fine. What will happen? This OB dash will go to the numerator and this EB dash will come to the denominator. Fine. So I can write down this can be written as equals to your OB dash will go to the numerator divided by your EB dash will come to the numerator. Sorry, it will come to the denominator. Fine. So your M can be written as the ratio of OB dash by EB dash. Now let's go back to your figure. Okay. Now if you look carefully, what does this OB dash denotes? It denotes the focal length f naught. And since it is in the direction of the incident light, so it will be a positive. Fine. What about B dash E or EB dash? EB dash denotes your object distance for the eyepiece. Okay, let me just write down here. This is the object distance which is denoted by UE. Fine. So EB dash is the object distance denoted by UE. And in this case, this will be positive or negative? It will be negative since it is in the direction opposite to the incident light. Fine. So let me write down. According to sign convention, your OB dash represents plus focal length of the objective. And your EB dash denotes the object distance for the eyepiece and it is negative. Fine. So now let us substitute this values here. Then I can write down my magnification m equals to the focal length FO minus UE. Fine. So I can also do one thing. I can send this negative sign in the numerator. Fine. So this represents the magnifying power for your astronomical telescope when the final image is formed at infinity. Fine. So let me put this in a box. Fine.